So welcome back, everybody. Let's continue this afternoon after the great talks we had this morning. Let's keep on with the Lambda service. We are all quite familiar with the AWS serverless compute service Lambda. You just have to write your code. You don't care about concurrency. You don't care about throughput. Just write your code. It works, and that's it. That's great for starting applications. But we, as developers, we are kind of frustrated to see like this kind of gray or black box, and we don't know how it works behind. But today, we are thrilled to have a serverless advocate at AWS with quite a background. He has worked for 25 years on multiple companies, from startups to global groups. And he's here today to tell us more about Lambda concurrency and throughput. Please welcome Julian.
Merci, c'est gentil. Bonjour, c'est moi avec le cheveu court ou non? Désolé, c'est le lockdown. Hello, everybody. Well, welcome to Serverless Days. It's awesome to be here. I do hope that you've had lunch, some cheese, some ham, petit pot de chocolat de mousse. Si tu as commencé d'être fatigué, c'est vrai, c'est l'après-midi, j'ai une idée. Chaque fois que je dis Lambda, levez là le bras, comme ça. Lambda? Parfait, parfait. Après, c'est le bon gym. So for the English people, it's after lunch. I know you're going to be tired. It's been some good French cheese, some all good things. If you're going to get tired, I'll understand. I'm not going to point you out in the audience if you're sleeping, unless you're snoring. And so each time I say Lambda, you can raise your arms, and we can do a bit of gym and get excited. So, thanks for the great introduction. My talk is about understanding Lambda, scaling, and throughput. Perfect. That was the first test. We're doing well. We're doing well. So, I think a lot of us in the room here know all about Lambda. You know, you Sorry, organizers, can I have 45 minutes for the talk, not half an hour? Because each time this is going to be Lambda, Lambda, Lambda. So, with Lambda, you provision your code or your image, and we just run it as a well-architected service in the cloud. So many kind of things you don't need to think about. You pay by the millisecond, all kinds of languages. You can do, Java, Go, and Node. Certainly, you can do PHP, as Mr. Napoli would advise you to do. With custom runtimes, you can literally run any language in the cloud. And of course, you don't need to provision or manage servers. I liked Emre Sandon talking earlier about babysitting servers. That sounds much more understandable than just talking about managing servers, how boring, it's babysitting. And the important thing is scaling up in milliseconds in response to traffic. And this can be traffic that's planned or unplanned, and that's one of the magic bits of Lambda, is how it is able to scale up. So I'm Julian, I'm a developer advocate, as I was lovelily introduced. Spent far too much in IT, and I worked in a lot of infrastructure, worked with a lot of servers, and then just couldn't wait to get rid of all the servers, so I didn't have to do any babysitting. I do enough babysitting with my own kids. So let's just talk about the Lambda request lifecycle initially and how some of it works. So the first part is there are two invocation models with Lambda. And one is a synchronous request. The caller calls Lambda either directly or via an SDK call or via CLI, also by something via application load balancer or API gateway, or even the new Lambda function URLs. And this is a request that goes to the Lambda function. Lambda function does some processing and then waits for a response and then returns it back to the client. Then we also have the asynchronous event process. And this is where you a caller application, and this can be yourself, or it can be an integration, such as with S3 or EventBridge or SNS, and that's just going to send a message to Lambda. Lambda's going to receive the message, acknowledge it, send back to the client, I've got your message, and then Lambda takes over the rest. And internally, what that actually does is Lambda puts that event on an internal queue. It's actually SQS behind the scenes, so nothing really magic. And then the Lambda service is going to take those messages off the queue and process your Lambda function. So two different ways that you can invocation models. The third way, which you can also use Lambda, which uses parts of this, is the event source mapping. And this is really powerful. So all on the left-hand side, the event sources, Lambda runs a polar service. And these are a bunch of polars that we run on your behalf. And we can pull messages from all these services from you. We can then filter them up, optionally filter them, so you can not process messages you don't need to. We can then batch them up and send those batches off to a Lambda function. And the cool thing about this is you don't need to manage those polars yourself. In fact, you don't see the polars. You've got no visibility of these polars because you don't need to. And the cool thing is you don't even need to pay for the polars. Lambda just runs this as part of the service. It's just what it can do. So a lot of great functionality if you're integrating with a lot of these event sources. So let's look at now the Lambda lifecycle in a sort of time span. And there are three parts of the Lambda lifecycle. There's three different phases. There's the initialization phase, the invoke phase, and the shutdown phase. So the initialization phase is where Lambda is going to set itself getting ready to run an invoke. And behind the scenes, it creates what is called an execution environment. And this is a secure, isolated runtime within a micro VM. So it's using a sort of hardware virtualization to spin up a micro VM in milliseconds to then run your Lambda function within that. It then is going to download the code, it's going to initialize any Lambda extensions, and these are sort of companion processes you can use with Lambda. Don't need to get into that today, but they can be helpful for you. It's then going to initialize the runtime, so that includes Node or Python or Java or any other kind of language, and then the sort of AWS part is done. And then what it's going to do is, in your Lambda function, it's going to run the code outside the handler. So this is where you're going to initialize maybe libraries, you're going to pull a secret in, you're going to connect to a database, do all the kind of preparatory stuff before the invoke. And then the invoke phase starts. And this is when your actual handler method within your function is going to run. Now, you might have a big function with a lot of different handlers. That's possible. And so it's going to run the individual handler that you're going to need. And then this first part of the initialization phase and the first invoke is what's commonly called the cold start. And this is the first time Lambda is then sort of ramping up, ready to get to manage your applications. And then the second time an invoke happens, because that initialization phase has already happened, it's called a warm start because it's all nice and warm and ready. There's nothing to heat up. And Lambda is just going to be able to run that invoke. And obviously, that is going to be quicker each time Lambda is going to invoke your function. And then behind the scenes, after a certain amount of time, Lambda then spins down that execution environment just to keep it or the environment fresh and do some balancing. And so Lambda just shuts down kind of things, and you don't really need to worry about that. That's just something that Lambda does in the background. But there's sort of two parts to think about it from how Lambda works. And the part of it I mentioned briefly before was the part that AWS handles, and then the part that you handle. And this is where you can optimize your code to be as fast and efficient and cheap as you can with Lambda. So we're obviously here talking about Lambda scaling, and there's been talking even in the intro today about how Lambda scales, and this is one of the benefits of Lambda. We can see here a graph here that not much work is happening, and all of a sudden, out of nowhere, a huge big spike happens. So how can you plan for this, and how can you even understand this to plan for it, to test for it, to make sure that it's going to be successful in your application? And all of that is actually, the main crux of it is understanding this concept called concurrency. And concurrency is the number of requests that your function is running at any time. Think of it as sort of parallel processing. So Lambda doesn't scale up. It doesn't add more memory or add more CPU dynamically to your function. It scales out by adding more instances of your function to do your processing. So when your function is invoked, Lambda is going to provision that instance, and then as more invokes come in from those various event sources, be it synchronous or asynchronous or the polars, it's going to spin up more execution environments. Now, there's also another concept with those polars. If you're pulling a batch off something and sending it to a Lambda function, that's still only a single invoke. It may have 10 records, it may have 10,000 records in the batch, but it's still an individual invoke. So let's look at the timeline graphically. Sometimes makes a bit more sense to understand this. So following the timeline, a single request is going to come in, and Lambda is then going to run the initialization cold start and then invoke the function. And as the function can only handle one request at a time, the execution environment is then blocked for this time. Can't do any other processing. And now, if the function is then invoked again, while the first request is still being processed, another execution environment, another instance of that Lambda function is created, and that's going to increase the function's concurrency. Then when the function code finishes running, it's then able to handle another request. And here you can see that request 1 has actually finished. And now, so that's warm and free to be able to be used. And as you can see, before that happened, request 4 and 5 was just spinning up more execution environments. So this process literally continues. As subsequent requests are going to come in, Lambda's going to reuse execution environments if it can, and if it needs to scale up, it's going to create new execution environments, and this all happens automatically. And this creating of new execution environments is concurrency. So if you think of concurrency, which you can count, and that's the number of simultaneous or parallel requests happening at a point in time. And so for a single execution environment, if it's being reused any number of times, the concurrent request is always going to be 1. But here you can see how it fluctuates as the cold and warm starts are happening, and you literally can just, where the line is count the number of execution environments that are processing requests, and that is going to be your concurrency. So 3 up to 5 goes all the way up to 6 when it's really busy, and then is automatically the concurrency is going to be reduced as you go down. So the thing to bear in mind is the concurrency is a point-in-time measurement, literally to the millisecond, exactly what Lambda is doing, the number of execution environments, and you're going to measure it. And that's not necessarily the same as, well, it's not at all the same as transactions per second, although they obviously do work together. So how do we understand transactions per second? Well, funny enough, transactions per second is exactly what it says on the label. It's the number of transactions that happen in a particular second. So, and it's the sum, basically, of all of the invokes that are going to happen in that period of time. So here we can see that we've got a Lambda function that takes 1 second to run, and then 10 invokes are going to happen concurrently. So what does Lambda do? It's going to create 10 execution environments, and then Lambda is going to then process those 10 requests per second. But now, if the function, for example, is halved duration to half a second or 500 milliseconds, then Lambda is going to reuse those execution environments. So there's still only going to be 10 execution environments processing those requests. However, because they are going to be reused, the transactions per second is going to be 20. So concurrency is still going to remain 10, but Lambda has used each of them twice, so it's going to be 20 transactions per second. And it's interesting to then think how that scales. Now, when Sheen was talking earlier, on one of his slides, he was talking about, Sheen and Silver were talking about how their shopfront was scaling up to handle incoming requests. And I think their slide said something like 1,000 transactions per minute. Now, I mean, Lego is a successful web company. You know, they're doing pretty well, I would hope, doing 1,000 transactions a minute. But they only had 150 concurrent Lambda functions. So you can see that a successful store, if your business is doing 1,000 requests every minute, and you're only then using 150 Lambda functions, you know, Lambda can scale up ridiculously high, so you can see the sort of ceiling we could get to. So there are 2 different other kind of things to be able to control some of this concurrency. And the first is a powerful thing called reserved concurrency. Reserved concurrency does 2 things. First of all, it's going to guarantee that Lambda can always scale up to that reserved concurrency limit. So if I set reserved concurrency 2, or I set reserved concurrency to 2,000, whatever that's going to be, Lambda is going to protect that resource and say you always have the concurrency to go up to that reserved concurrency amount. But it also gives you 2 additional helpful things that you can do. You can use this actually as a limiter to protect downstream resources. So if you have a database connection that can only handle 20 connections at a time, or you've got a third-party API that does whatever it needs to do, connect a payment or do something, and it can only handle 50 concurrent requests, well, you can set your Lambda concurrency to limit what that downstream resource can do. So Lambda will just send back to its caller, I'm throttling, a 49 response, I'm throttling, and so you won't be able to overwhelm that downstream resource, which can be super useful. And the other cool thing is you can actually set concurrency to 0, and that just sets Lambda as an off switch. So whatever is calling Lambda will just get a response from Lambda going, sorry, I can't do anything, I'm busy at the moment. But it means if you need to, you've got something that's broken on your downstream resource, something that's timing out, or something that you need to fix, you could, in a number of scenarios, pause Lambda, fix what's going on in the background, and then dial up that concurrency again, and Lambda will continue processing. And obviously, you've got to handle retries and throttling and backoff, all that kind of thing. But it is possible to use this really cleverly, that you'd be able to use Lambda in a nice way to pause Lambda to be able to fix things in the background. OK, I'm a few minutes in. We haven't had any hands going up, so I'm going to have to say Lambda again. Excellent. I hear no snoring, so I think we're doing OK. Good job. So the other one is provision concurrency. So this is really useful for mainly synchronous requests. And this allows you to set a minimum number of execution environments for a particular published function version. So This, in effect, actually runs that cold start process in advance of when you need invokes. So if you have a sale happening at 9 o'clock in the morning, or you have a talk that's happening at 4 o'clock in the afternoon, and you're going to have some sort of special that you know your website's going to be absolutely slammed, you want to be able to ensure that you've got enough execution environments available. So what you can do is you can pre-warm those up in advance. And this is obviously, as I said, mainly only useful for synchronous requests. For asynchronous requests, well, those aren't time-bound anyway. You would be wasting time, money, and a bit of effort setting up provision concurrency for asynchronous requests. But of course, there's not a limit to this. You can use provision concurrency to set up, maybe you need 100,000 concurrent invokes, build that all up over time, and then if you exceed that, you can still use the burst concurrency, which I'll cover shortly, to handle those additional invokes. So this is a nice protection mechanism to make sure whatever you're building is as responsive as you need it. So then there's a burst concurrency quota. So this is when Lambda is doing absolutely nothing, the function has never been invoked. All of a sudden, you've got an influx of invokes that come in. Lambda's going to scale up to a maximum of 1,000 concurrent execution environments without you having to do anything. That's in the bigger regions. In some of the smaller regions, it's going to be 500. But this, you don't have to plan for. You don't have to do anything. Lambda will just scale up to between 500 and 3,000 execution environments, depending on the region. And then after this initial burst, each additional minute, Lambda adds another 500 execution environments it can spin up. So you can see the sort of graph will be going up, and I will cover that graphically. It'll make more sense. So there's also an account concurrency. So within your account, per region, there is an account concurrency, and this is shared between all functions in an account in that region. And this defaults at 1,000, which I know is pretty low, but I mean, this can literally be increased to hundreds of thousands. We've got many customers who have an account concurrency of hundreds of thousands. Now, remember that reserved concurrency I spoke about earlier, which then guarantees concurrency execution environments from the Lambda service? Well, this is how this works from the account concurrency. So you can see the account concurrency for all the functions in an account. You can think of it as a pie graph, which is going to be a bit easier to understand. And then each function you allocate reserved concurrency takes its little slice from the big account concurrency pool, and that's how you can see how Lambda functions would be protected, and all the rest of your Lambda functions then would use the remainder of your concurrency. So some scaling. So let's sort of graphically walk through the scaling quotas and see how they work. Maybe that's going to be a bit simpler to understand. So anticipating handling additional load, the application builders have already raised their account concurrency from the default 1,000 up to 7,000. So they were planning ahead. They knew something was going to happen. They've raised their account concurrency to 7,000. And now there are no other functions in this account, just to keep it simple. And so it can use all of that available pi, all of that available account concurrency. So then, just before 9 o'clock, the application already has a steady stream of requests, and it's using 1,000 concurrent execution environments. And then, say in this example, each Lambda function takes 250 milliseconds, so the transactions per second would be 4,000. So 4,000 times 1,000 times 4, you've got 4,000. So at 9 o'clock, there's that big anticipated spike in traffic of 5,000 sustained requests. It was a little bit more than expected. They were planning, but let's see how it's going to handle it. So 5,000 sustained requests come in. So 1,000 requests are then going to use the existing execution environments, and Lambda is going to use that 3,000 scaling. So we're running in a big region over here. Lambda can immediately scale up to 3,000 burst concurrency to create new execution environments to handle that load. Now, 1,000 requests are going to be throttled because there's not enough burst concurrency to handle all 5,000 of those requests, but still, it's still at pretty high scale because if you remember, the Lambda functions run at 250 milliseconds, so immediately we're already able to handle 16,000 transactions per second. That's going to be pretty high up. So in the next minute, Lambda is going to scale by another 500 concurrent invokes per minute. That burst is going to get another 500, but 500 requests are still going to be throttled. And then the next minute, Lambda is going to scale by another 500 concurrent invokes, and now no requests are going to be throttled. So the application is now going to be able to handle all 5,000 requests, and this could literally carry on forever. But now the sale was particularly good, and 5 minutes past 9, there's an unexpected load that's going to happen. 4 minutes past 9, sorry. So the app sees another huge big spike in traffic, and this was, unexpected. So 3,000 new sustained requests are going to join the Lambda party and happen. Let's see what happens. So we've got now a total of 8,000 requests coming in. So 5,000 of those requests are going to use the execution environments that we're already running. And now Lambda is going to use the burst concurrency that is built up over 2 minutes, which is going to be another 1,000 concurrent invokes. So we've got the 5,000 plus the 1,000 from the burst concurrency. But there are two limits that are then going to kick in over now. There isn't enough burst concurrency, so 1,000 of those new requests are going to be throttled as well. And then now also we're hitting up against the account concurrency limit, and so another 1,000 requests are going to be throttled because that has since been reached. Remember, in the beginning I said that the application planners had planned for 7,000 account concurrency, so we've bumped up against that limit. But now, in another minute, Lambda is going to be able to scale up to another 500 requests because that burst concurrency limit has been raised, but that account concurrency is still going to throttle 500 requests. And where are we? In the last 6 minutes past 9, Lambda is going to be able to scale up by another 500 requests, but that limit of 1,000 concurrency has still been reached. And so, the app will continue to handle the sustained 7,000 requests, but at the moment, 1,000 requests per second are always going to be a throttle because of that account concurrency. But of course, that can be raised easily, and that can be done in the service quotas console. So, it's not a support call. This is a really quick thing that you'd be able to raise. So, in 7 minutes, the function has scaled up from 4,000 requests per second to 28,000 transactions per second. So that's pretty quick. Now, the burst concurrency I did talk about is fixed at 3,000. We do have some large customers which we can work with, which can possibly increase that if you need it, but it needs a sort of decent amount of work to understand your use cases and whether there are other ways to use that. So I talked about concurrency and the invocation models. Let's sort of see how they match in together. So with an asynchronous request and a synchronous request as well, it's just a one-to-one mapping. And it's pretty simple. A single event, you've got one Lambda invoke per event. So if you're behind API gateway, invoke a Lambda function, one request comes back, and you're done. If you're using asynchronous via Event Bridge, for example, or S3 notification, Event Bridge, a single rule, it's going to go to a Lambda function, and it's going to do its thing. Now, on the polling event source mapping, sort of two different ways this work. One is for queues, so that is something like SQS, and that's going to take something off the queue and it's going to send a batch to Lambda. So that's one Lambda function is going to be invoked for every single batch. Now, the stream event source mappings, and these are things like Kinesis or with Kafka, this can scale even faster, even quicker, because Kinesis and Kafka has this concept of shards, and these are partitions. And so you can, when the producer sends a message to the stream, it can decide which partition that's going to go onto, and then Lambda is going to invoke a Lambda function per that partition, per that shard, but also per batch. So every single partition, every single shard is going to have its own unique Lambda function, which is going to be able to pull a batch off that Lambda function. So just helps to understand how Lambda scales for the different invoke models. Let's actually walk through how this works with SQS. So SQS and Lambda work really well together. It's a really good way to use SQS as a buffer. If you're unsure how many messages you're going to do, or you just want a storage area where you just need to keep messages until they can be processed, SQS is great. It has unlimited scale. Even knowing some of the figures internally about SQS works, the mind boggles about how scalable SQS is. And it was literally one of the first services that AWS built. So here we've got a producer application which is send message A, B, C, and D. There are 4 messages onto the queue. And how does Lambda work with that? Well, as I said before, Lambda runs this Polar service on your behalf. It's all abstracted. You don't need to see it. And this is going to pull messages off the queue. So the batch size for this example has been set to 3. So Lambda is going to pull 3 batches off of the queue. And the batch of 3 is going to go to the Polar, and it's going to send a single one batch of 3 messages to the Lambda function. So that's one invoke, one execution environment containing 3 messages. Then the long polling is going to happen because the batch size was set to 3. There's another message available on the queue. So the Polar is going to grab then that single message and send that to your other Lambda function, which has going to only have a batch of 1. But now, the batch of 3 gets processed successfully. So the Lambda Polar on your behalf then is going to delete those messages off of the queue. If there were any failures within that batch, you can also optionally tell Lambda to say, just delete those individual failed messages off the batch, rather than having to redo the whole batch, which was the process before. But in this instance, all the messages are processed successfully. That's all working, and all the messages are then deleted off the source queue. So batch 1 is still being processed, but there's an error. Something has happened. Maybe it's something malformed. Maybe downstream services has had some kind of issue, and your Lambda function does not then process correctly, or you generate an error. So what happens is, jump to slide. So what happens is this is concept in SQS of this visibility timeout. And actually, as soon as a Lambda pulls a message off of the queue, it sets that visibility timeout which starts. And that means nothing else can pull anything off pull that particular message off the queue until the visibility timeout ends. And that's just a way to protect processing duplicate messages. So the message is not deleted from the queue. When that visibility timeout then ends, SQS goes, I have another message available for you, dear Lambda function to process, and that batch is going to be then pulled again from the polar, and something disappeared. That single message in the batch is going to be pulled from by the Lambda polar, sent to the Lambda function, and then in this scenario, it's then going to work, because maybe it was a downstream resource. So this is a really good way that you could use Lambda to automatically retry messages that have failed. And so there are sometimes going to be issues in your application where things just don't work, and the retry will happen automatically. Obviously, in a production application, you want to protect this, so you don't want messages deleted off the SQS queue. You want to make sure that you send it to a dead letter queue. Also on the Lambda function, if you've got, and you set that dead letter queue on the original SQS queue, by the way. And then also on the Lambda function, for some other kind of errors, you can use Lambda destinations or things like that to also send failed invocation results somewhere else, so you can always protect your messages. You never really want to lose any data. So we're talking about cold starts, and there are two sort of different aspects of cold start. Spoke a bit about this earlier. You've got the AWS part of cold starts and your part of the cold starts. So cold starts happen when you have more requests to your Lambda function. That's good. Business is booming. More things need to be processed. So these are things that you're going to control. And so when you scale up, when you send more events to Lambda, you've got more events processing from S3. You've got more requests via API. So also, when you then configure provision concurrency, that is then going to need to set up the invocation environments in advance, and off that's going to go. And also when you update your code in your configuration. But AWS also sometimes needs to do cold starts for you, because we manage it behind the scenes. The execution environments are refreshed, they're reused every now and again, so we need to do that. And then also, if there's a failure on any of the worker hosts, Lambda still does run on servers, even though it's called serverless. Don't tell anyone I told you that. But if those servers do fail, they need to be replaced, and obviously that's cold start will happen. But cold starts happen very rarely, actually, in big production applications. When you're a developer, you're coding, each time you upload your Lambda function, it's a new update code or config, and the cold start process is going to happen. You start to panic, you start to sweat, and that's not just from the cheese from lunch, thinking that, oh dear, when this scales up for my production traffic, it's going to be huge. But because of the execution environment reuse, it's going to reuse those execution environments. Your cold starts, generally in decent-sized production applications, is way less than 1%. And there's no cold start penalty if you're using VPCs. That used to be the case, now no longer. So you don't have to worry about connecting Lambda functions to a VPC. So optimizing cold starts is all about, first of all, performance testing to find out what your baseline is, and then is to minimize your initialization time. And this is the cold start, and basically, don't use it if you don't need it. Don't import big packages, use smaller streamlined SDKs, try and remove everything in your code to make it as small as possible. Minimize the duration of your Lambda function. You can reuse expensive operations, so fetch that secret in the init part of your function and then just reuse it in the handler. Make the database connection once and reuse it, and all those kind of things. And then if you completely want to get rid of cold starts, well, you can use provision concurrency, or you can use snap start for Java. And this is a really cool functionality with Java, where basically you run the cold start, it creates a snapshot, and then when you need to invoke that function, it's going to rehydrate that snapshot, which literally takes a few milliseconds, and run your Java functions without any cold start penalty. Super cool functionality. I suggest you, if you're a Java person, having a look at that. So there are lots of metrics you can do. Obviously, you want to make sure that Lambda is behaving as you expect. You can look at errors. You can look at throttles to understand what's happening. And then also the concurrent executions and the provisioned concurrent executions. That's a mouthful. But that's basically the count I was showing earlier. You can monitor that and see exactly how many concurrent requests are happening. And when you do your load test, check your concurrency, and then you can decide if you need to increase your limits as well. And then other metrics, if you're using SQS or Kinesis, they're all a whole bunch of metrics to understand the scaling and throughput that's going to go over there. So just some synchronous invocation best practices. Do your load testing beforehand. Find out how high your Lambda can scale. Maybe Lambda's not going to be the bottleneck. Maybe you're going to be pulling something from an external API or even another AWS service that has a limit. So do your load testing. To find out what that's going to happen. Set the appropriate timeouts so your Lambda functions don't unnecessarily run for too long. Remember, behind API gateway, there's a 29-second response limit for API gateway. So time your Lambda functions appropriately. And then also look at your backoffs. There's some really good papers that AWS has provided as well, all about retries and backoff and jitter. Sounds all weird kind of words, but it means that you're not hitting your API regularly. If something's going wrong, you sort of slow down your requests not to overwhelm your API. And there was a great talk earlier. Luke was mentioning idempotency and all those kind of things, really important in any event-driven applications when things are distributed, so do your idempotency. Quickly on to asynchronous, some best practices. Use async when you can. Really use async when you can. That's going to be one of the powerful things of Lambda. There's lots of configuration of your Lambda function. There's batch sizes. You can use batch sizes up to 10,000 with SQS. 10,000 messages in a batch. You've got 15 minutes to process them. A lot of things you can do in the batch. The on destinations I mentioned, doing the monitoring, and then the SQS queue configuration. So I'm done from all the big technical talk. I can take a breath. Please go and visit Serverless Espresso downstairs. This is Michael and the team have put together. I've been showing it. It really shows how to build an event-driven application. Uses not what we've discussed today, but a lot of event bridge and step functions to build that. Really cool, useful stuff too. And you get a free coffee out of it as well. Also, we've got serverlessland.com. This is a one-stop landing page for everything to do about serverless on AWS. Huge amounts of code examples. There are some new learning guides which are going on. There's a Java replatforming one, lifting and shifting a web app to serverless. Lots more content being added all the time to serverlessland.com. A really cool spot. But merci. I hear no one's fallen asleep. Thank you so much for joining today. It's a pleasure to be in Paris again. Absolutely love coming to Paris. And Serverless Days, to the organizers, have put on such a good show. And what's a bit weird now is I'm going to have to hand over to another colleague who's going to tell you when you don't need to use Lambda. So you can use this talk and Jerome's talk and put them together. But yeah, hopefully it's been useful. I haven't really got time for questions now, or do I?
I think we can have like 1 or 2 questions.
Oh, 1 or 2 questions. But if not, I'll be around all afternoon and a bit this evening. So any questions, happy to answer.
Any questions?
Any questions? Mexican wave. Yeah, we could have done that instead of the...
Maybe I have one. So you talked at the beginning of the presentation about the reserved concurrency you can put on a single Lambda.
Yes.
And you talked about the use case of having, for example, a database with a certain amount of allowed connection. Is it possible, for example, or what do you recommend if you have different Lambdas talking with this database? Do you have like kind of a reserved group Lambda concurrency or something like that?
Yeah, definitely that is a consideration. You've got multiple Lambda functions, maybe even in different accounts, talking to the same database. That is a challenge to manage. I don't have an easy answer in terms of what Lambda can do, but something like RDS proxy can be certainly an advantage. RDS proxy is an AWS service where multiple Lambda functions can connect to the RDS proxy as a service, and then that maintains a single connection to different databases. But also, I work in the product team. We also love getting feedback from people. So we have specific requests for how you would see this kind of work happening. I know the product team are thinking about concurrency and are thinking about bursts and requests and everything at the moment. And trying to find better ways to be able to support you in your concurrent needs.
Great, thanks.
Any other questions? No? Good. I'll be around. So thank you very much.
Thank you very much.